Hi, everybody. This is our one of our recordings for the class that will cover some of the uh, week 10 stuff. So week 10, we're doing indicators of validity and credibility. We have a variety of concepts that we started in week 9. Um, and we have three short extra readings here on three topics. One we've already dealt with, which is the difference in difference specification. I've written that up here in a short PDF so that you'll have a another version of that to read. Uh, I've made a video about conditional mean independence, which is another assumption that we make for ordinary least squares. And there is a video about that right here. So you can read it. It's a short reading about what this conditional mean independence assumption is. And you can then watch the video of that. Uh, Today, this video, I'll talk about what we call joint hypothesis tests. And this video then will be added to this week 10 list. So joint hypothesis tests is our topic for today, and you can read about it right here in this PDF. It's about 5 pages long, covers the idea of what if we want to do tests of joint hypothesis, not just a single hypothesis about a regression coefficient, but multiple regression coefficients, testing them jointly. So we'll explain what we mean in a second. So let's get started then. And I'll make this full screen. So here's a very short introduction to joint hypothesis tests. You can read more in the reading. So let's suppose we have a regression equation like this one that we have here. Let me get my pen here, right? So we have y equals b0 plus x1, b1 times x1 plus b2 times x2. And we want to test the joint hypothesis that b1 equals 0 and b2 equals 0, that both of these coefficients, both of them are equal to 0. How do we test that hypothesis? So remember, that's different from our earlier usual test. Our earlier usual test is the test that B1 equals 0. So to conduct that test, we construct a test statistic, a t-stat, and we know that that t-stat follows the standard normal distribution. And so if the null hypothesis is that the coefficient's equal to 0, then 5% of the time we'd have a t-stat value greater than 1.96, and we'll say that that's would be relatively low probability. And so if we do find a t-value, t-stat value greater than 1.96, we'll reject the null hypothesis. Alternatively, right, of course, we could test the null hypothesis that beta 2 is equal to 0. So those are our separate null hypothesis, separate hypothesis tests under assumptions that one of the coefficients is equal to 0. Now we have a different hypothesis test. We want to test the joint hypothesis that both of them are equal to 0. So how do we test this? That's the question that we're asking. And what we would like is an estimator or a test statistic such that if the null hypothesis is true, if they are both equal to 0, then there'll only be a 5% chance that we would reject the null hypothesis. So let's assume that they're both equal to 0. That's our null hypothesis. Whatever test statistic we construct, we would want it to be such that at most 5% of the time, if the null hypothesis were true, we would calculate that test statistic value from our sample and reject the null hypothesis. So with those preliminaries in mind, let's consider a bad test statistic, a way to test this joint hypothesis. Suppose we say that we'll reject if either the test the t-stat for coefficient 1 is greater than 1.96, or the test statistic for beta 2 is greater than 1.96, or both of them are greater than 1.96. So we could say, how do we test the joint hypothesis that they're both equal to 0? We could say, well, if we reject for this one, or we reject for that one, or we reject for both of them doing the single hypothesis test, then that's when we should reject the joint hypothesis. Well, that's our proposal. Let's calculate what the probability is of that hypothesis. So that's the probability of rejecting our joint null hypothesis. That's the probability that T1 is greater than 1.96. Or the probability that probability that T2 is greater than 1.96, or the probability that T1 plus T2. I think I should have said or here, right? We have the ors here, so I'm not sure what I said now, but should be ors, right? So this is the same thing as 1 minus the probability that neither T1 and T2 are greater than 1.96. So that's the probability that T1 is the t-stat for coefficient 1, the single hypothesis test is less than 1.96, and the t-stat for beta 2, the single hypothesis test that beta 2 is equal to 0 is less than 1.96. So we can see that these two probabilities are equivalent because there's only 4 possibilities that T1 is greater than 0, but T2 is not. T2 is greater than 0. Greater than 1.96, but T2 is not greater than 1.96. T2 is greater than 1.96, but T1 is not greater than 1.96. They're both greater than 1.96, or neither T1 nor T2 is greater than 1.96. Those are the 4 possibilities, and they have to add up to 1, the 4 probabilities. So 1 minus this is the same thing as this. But what is the probability that T1 is less than 1.96 and T2 is less than 1.96? If we assume these T statistics are independent of each other, that's just the 2 probabilities multiplied by each other. And we know that the single coefficient T statistic is calculated such that the probability that T1 being less than 1.96, that's 0.95, because being greater than 1.96 is 0.05. So being less than 1.96, an absolute value, these are all absolute values, right, is 0.95. So we have 1 minus 0.95 times 0.95, 1 minus 0.9025, that's 0.0975. So this estimator that we propose here leads us to reject the null hypothesis almost 10% of the time. So that's too easy a test. We reject the null hypothesis too often if that's our test statistic. So we're not going to use that test statistic. We've just shown that that's not a valid test statistic. This idea of being too easy a test, right? It's sort of like saying when you're playing any kind of game against an opponent, that you say, oh, every time the opponent scratches their nose, I know I'm going to lose that point, so I'll give up. Every time the opponent scratches their nose, I'll lose that point, so I'll give up. Most people would say, well, that's kind of a dumb way to proceed with your game because many times your opponent is just scratching their nose. They don't have a advantage winning thing that they're going to do in poker, especially. I'm thinking about that. That's called the tell. And you wouldn't want to use that as your criteria for how you play the game. So in this case, this test statistic we're constructing here is not a good test. We'd reject the null hypothesis that they're both equal to 0. We'd reject it too often. So we need a different test, is the idea here for this joint hypothesis test. So we have, I'm going to go on, we have 2 different tests we can do. And if we just have 2 coefficients, this is one test we can do. We can calculate something that we'll call an F statistic, If there's just x1 and x2 in the coefficient, we can calculate the t-statistic for coefficient 1 and square it, the t-statistic for coefficient 2 and square it, and then subtract 2 times, and you don't need to memorize this, 2 times the correlation between these t-statistics. So we have this complicated formula that you do not need to memorize. But the key part of this formula is that if the 2 t-statistics are correlated, notice that we're subtracting that from here. So the f-statistic will be lower. And now we'll reject the null hypothesis if the f-statistic is high. We'll reject the joint null hypothesis that both are equal to 0. But let's think of a different test. So that's one. There's several tests here, but the more interesting test, more intuitive test is this test. So we'll imagine we have our coefficient with x1, x2, and x3, and we want to test that beta 2 and beta 3 are equal to 0. So what we're going to do is run this regression with and calculate the R-square for that. What's the overall explanatory power of including all 3 variables, x1, x2, x3? And then we're going to estimate what we'll call the restricted regression. So we're going to assume that beta 2 and beta 3 are equal to 0. So if beta 2 and beta 3 are equal to 0, there's no need to include x2 and x3 in the regression. So we just run the regression with x1. That's what we'll call the restricted regression, and we'll calculate the R-square for that. So now we have 2 R-square, the R-square for the restricted regression and the R-square for the unrestricted regression. And it's pretty clear, remember, the R-square always goes up when we add more variables. So this always has to be bigger than this. The unrestricted R-square has to be bigger than the restricted R-square. But maybe if x2 and x3 don't actually have 0 effect on the outcome, then the R-squares are going to be very close together. So we'll calculate what we'll call an f-statistic as the difference between these 2 R-squares. The difference between these 2 R-squares. So if the unrestricted R-square is a lot bigger than the restricted R-square, the f-statistic will be larger. If the unrestricted R-square is pretty much the same, just a little bit bigger, the f-statistic will be very small. We'll divide that. We have to normalize this so that it follows a standard distribution. So we divide it by Q, the number of restrictions. And then the denominator, we put 1 minus, remember the R-square varies between 0 and 1. So we put 1 minus the unrestricted R-square, and that in turn divided by n minus k minus 1. N is the sample size, k is the number of regressions. So Q here is the number of restrictions, k is the number of regressors. So this is the key test statistic for testing joint hypotheses. Let me erase here. And essentially, right, it's the difference between the unrestricted R-square and the restricted R-square. The bigger that is, the higher is the f-statistic. The f-statistic follows a distribution called the f-distribution, and we don't need to know very much about the f-distribution. You did study it in your Math 8 and your Almost 40 class, your earlier statistics class. There's the normal distribution, the chi-squared distribution, the f-distribution, and the beta distribution. Those were distributions of random variables that you studied in your earlier statistics class. We won't need to ever look that up, although you might. And in the chapter, I show you how to do that in R. So if you wanted to, in your Econ 42 class, do a joint hypothesis test, you could do that using R. So I think we don't have much else to do here except look at a little numerical example. So if the unrestricted R-square was 0.85 and the restricted R-square was 0.75, and there were 2 restrictions, so beta 2 and beta 3 both equal to 0 would be 2 restrictions, and we had a sample of 155 and we had 4 explanatory variables, what would be the R-square? So we have R-square, the difference here is 0.10, 0.85, and 0.75. The difference is 0.1. 0.1 divided by 2 is 0.05. So that's our numerator. In our denominator, we have 1 minus 0.85, so that's 0.15. And then we have 155 minus 4 minus 1, which would be 150. So we do all that calculation, we get an F statistic of 50. The rule of thumb for F statistics is if it's bigger than 3 or 4, we will reject the joint null hypothesis. This is way bigger than that. So we will reject the joint hypothesis that beta 2 and beta 3 are equal to 0. And again, that's the rule of thumb for the F statistic. If it's bigger than 4 or so, we'll reject the joint null hypothesis. I think, let me see, did I have anything else here in this? Here's another version of it, a little clearer. Remember the R square is the R square is 1 minus the sum of squared residuals divided by the total sum of squares. So if we can rewrite the R square, since everything shares the total sum of squares denominator, we can just get rid of that. And now we have the reverse order since it's 1 minus. So it's the sum of squares of the restricted regression is another version of the formula minus the sum of squares of the unrestricted. So again, it's the sum of squared residuals. The difference, sometimes you see the formula written this way, but this and this are exactly equivalent. So there's no just if you're interested, it's worth taking a look at. And I think that might be all for this. You may want to read this chapter and review this video again carefully, especially review the numerical example that we did here, and be able to calculate. You should start noticing now that in your R, in model summary, it will give you the F statistic for the joint hypothesis that all of the coefficients on all of the included explanatory variables are equal to 0. So that will always be in the model summary display of the regression results.